in section 6.2, we're going to look at what happens when we're solving a system of equations using Gaussian or Gauss-Jordan elimination, and either there isn't a solution or there are an infinite number of solutions. So number one, apply Gaussian or Gauss-Jordan elimination to systems without unique solutions. Either there isn't a solution or there are an infinite number of solutions. The second thing we're going to do is use Gaussian or Gauss-Jordan elimination to solve a system where we have more variables than we do equations. To be able to solve a system for a unique solution, we must have the same number of equations as we do variables. So if I have 3 variables, I must have 3 equations to be able to find a unique solution. So what happens if I have 3 variables and I only have 2 equations? Inconsistent and dependent systems. My sharing is not working, so let me see if I can fix that. All right, here we go. Inconsistent and dependent systems. We can use Gaussian or Gauss-Jordan elimination on systems with 3 or more variables to determine how many solutions such systems may have. In the case of systems with no solutions, it's inconsistent, or infinitely many solutions, it's dependent. It is impossible to rewrite the augmented matrix in the desired form with zeros down the main diagonal from the upper left to the lower right and zeros below the ones. So what happens here? Well, let's write the augmented matrix. Let's go put this in our calculator and let's see what happens. This particular system has no solution. So let's see what happens when we put that in our calculator and use Gauss-Jordan elimination. All right, so I'm going to write my augmented matrix. My first column is the coefficients on my x's, 1, 2, 3. My second column is the coefficients on the y's, -2, -3, -4. The third column is the coefficients on my z's, -1, -1, -1. The fourth column is my constants. Okay, again, I'm going to check the augmented matrix, make sure I have it written down correctly by going by rows. I wrote the matrix down by columns. Now I'm going to check by rows. The first row should be 1, -2, -1, -5. It is. The second row should be 2, -3, -1, 0. The third row should be 3, -4, -1, 1. So now I'm going to go put that augmented matrix in my calculator. And I do want to show you here, if you've put in a lot of matrices, so you've been doing your homework and you've put a lot of matrices in your calculator, how you can delete those matrices. Before we put that augmented matrix in, let me show you that. So if I look right above the plus sign on my calculator, there's an MEM, that's memory. So if I do second plus sign, that'll take me to my memory maintenance. And I can go down to number 2, memory management delete, hit enter. And number 5 is matrix. And from here, I can delete my matrices. So here's a matrix that I inputted prior to this example, and I just can hit the delete key, and that deletes that matrix from my list. All right, so now let's go into our matrix menu, and let's put that augmented matrix in. So I'm going to go second inverse to my matrix menu. I'm going to arrow to the right, and I'm going to edit, and I'm going to put that matrix in matrix A. So I'm going to hit enter. And that is a 3 by 4 matrix. There are 3 rows and 4 columns. So 3, enter, 4, enter. Now I'm going to input the elements in those rows. So I had 1, -2, -1, and -5. Make sure when you're putting in a negative that you use your negative symbol, not the minus sign. All right, so the second row was 2, -3, -1, and 0. And I do have to type in the 0. And then what do we have? 3, -4, -1, and 1. And I'm going to do a quick check to make sure that I've inputted my matrix correctly. 1, -2, -1, -5, 2, -3, -1, 0, 3, -4, -1, 1. All right, now to use Gaussian or Gauss-Jordan elimination on this matrix, I need to first exit from the matrix menu. So I'm going to do a second quit and get out of there. Now I'm going to go back in, second inverse, and now you can see that my matrix, it has been inputted. I'm going to go over to math, and I'm going to go down. I could also go up and find it. And I'm going to use reduced row echelon form. So I'm going to use Gauss-Jordan elimination. Hit enter. Now what matrix am I going to perform reduced row echelon form Gauss-Jordan elimination on? Well, that was matrix A. So I'm going to go back to my matrix menu, number 1. So I'm going to hit enter, close my parentheses because that's a good habit to be in, and hit enter. All right, now let's look at the resulting matrix. The first row is 1, 0, 1, 0. The second row is 0, 1, 1, 0. So that should be a hint that something's wrong. Because if this were in reduced row echelon form, the second row should be 0, 1, 0. So I've got something going on. Now look at the third row. Well, now I have a problem. Because the third row says 0, 0, 0, 1, which says that 0x plus 0y plus 0z equals 1. So that third row says 0 equals 1. I don't think so. 0 cannot equal 1. So when something like this happens, when the third row in your reduced row echelon form, the first 3 numbers are 0, and the fourth number is something besides 0, this system has no solution. There's no way I can get 0 equals to 1. So I'm going to write this augmented matrix down on my slide. And let's go back and take a look at that real quick. Let me share. All right, so here is the matrix that we got from our calculator. And the third row of that matrix says 0 equals 1. That is not true. That is false. So this system has no solution. So we say it has no solution, it's inconsistent, or we can say that the solution is the empty set. So it's inconsistent, its solution is the empty set, it has no solution. All right, let's look at another system. Let's use Gauss-Jordan elimination to solve this system. So we have x minus 2y minus z equals 5. 2x minus 5y plus 3z equals 6. And x minus 3y plus 4z equals 1. Let's do this and let's see what happens. So I'm going to write my augmented matrix. And I'm writing down in columns the coefficients on my x, my y's, and my z's. And then in the fourth column, that is my constants. So I'm going to take a quick gander here, and I'm going to make sure that I have it written down correctly. By rows, I should have 1, -2, -1, 5, 2, -5, 3, 6, 1, -3, 4, and 1. And it looks good to me. So now let's see if we can't put this in reduced row echelon form. So I'm going to go put this augmented matrix in my calculator. Now, since I just put the previous matrix in matrix A, maybe I put this one in B. So I'm going to go to my matrix menu. I'm going to go over to edit, and I'm going to go down to B. And I'm going to put this matrix in B. It's a 3x4 matrix, 3 rows, 4 columns. And let's put in our elements. 1, -2, -1, 5, 2, -5, 3, 6, last row, 1, -3, 4, and 1. All right, let me make sure that I've got that inputted correctly. 1, -2, -1, 5, 2, -5, 3, 6, 1, -3, 4, and 1. Okay, I look good. So I'm going to exit from my matrix menu. Now I'm going to go back in, and I'm going to go over to math, and I'm going to find reduced row echelon form, which is B. And I'm going to calculate reduced row echelon form for matrix B. So I'm going to go back into my matrix menu and find B. That's number 2. Close my parentheses and hit enter. All right, look at what happens here. Look at the third row. The third row is all zeros. If the third row is all zeros, that means this system is dependent. 2 of my equations were actually the same equation. So there is no unique solution. There's actually an infinite number of solutions. So you have to write x and y in terms of z. All right, so if the third row in your augmented matrix, after you performed Gauss-Jordan elimination, put it in reduced row echelon form, is all zeros, then this system is dependent. And I need to write x and y in terms of z. So I'm going to write this down. Let me show you how to do that. All right, so here is the matrix up here to the right is the matrix after I've performed Gauss-Jordan elimination and put it in reduced row echelon form. So what I'm going to do is I'm going to take the second row of my matrix, so my second row here, and I'm going to write the equation for that second row. So I have 0x plus y minus 5z equals 4. And I'm going to solve that equation for y by adding 5z to both sides. So I'm going to move the z to the right-hand side of the equation by making it positive. Then I'm going to take the top row and I'm going to write the equation. So I have x plus 0y minus 11z equals 13. So x minus 11z equals 13. And I'm going to solve this for x by adding 11z to both sides. So x will be 11z plus 13. So I've written x and y in terms of z. So now how do I write the ordered triple, which is a solution to this system of equations? I'm going to write the ordered triple, x, y, z. X is 11z plus 13. Y is 5z plus 4, and z is z. So what does this mean down here at the bottom? It means for a particular z, I get some x and some y. For example, if z is 1, x would be what, 24, and y would be 9. If z is 0, x would be 13, y would be 4, and z is 0. So depending on what z is, we get a different x and a y. So this system is dependent. X and y depends on what z is. So when you solve a system of equations using Gauss-Jordan elimination, and the third row is all zeros, the system is dependent. You write the equation from the second row in terms of y, in terms of z. So we solve y in terms of z. That's your second coordinate in your ordered triple. Then you write the first row as an equation and solve for x, and that will be the first coordinate in your ordered triple. So x and y depends on what the value of z is. All right, what if I have a system where I have less equations than I do variables? So that is this example here. I have 3 variables, x, y, and z, but I only have 2 equations. Well, this system is dependent because I don't have enough equations to find a unique x, y, and z. But I can still solve this in terms of z by putting this in my calculator. So I'm going to write the augmented matrix. Now, in this case, I only have 2 equations, so I'm only going to have 2 rows in my matrix. The first column, 1, 1. The coefficients on the x's are 1. Second column would be 2, 1. Third column would be 3, 1. Fourth column would be 70, 60. I'm going to make sure that's right. Looks good. And this is a 2 by 4 matrix. There are 2 rows, but 4 columns. And I'm going to input that into my calculator exactly that way. It's going to be a 2 by 4 matrix that I'm going to input. All right, so let me go back to my calculator. All right, so I might as well put this matrix in matrix C since I've already used A and B. So I'm going to go to my matrix menu. I'm going to go over to edit, and I'm going to edit C, number 3. And I'm going to put that 2 by 4 matrix in. All right, so the first row was 1, 2, 3, and 70. And the second row was 1, 1, 1, 60. All right, make sure I have it inputted correctly. I'm good to go. So I'm going to exit from the matrix menu. Honest, I'm going to exit. There we go. Now I'm going to go back in and I'm going to calculate. So I'm going to go on my math menu, reduced row echelon form, which is B, on matrix C. So go back to my matrix menu and find matrix C, that's number 3. All right, so here is as best my calculator can do to get this in Gauss-Jordan elimination. It can't be in Gauss-Jordan elimination, reduced row echelon form perfectly because it's a dependent system, so it's not going to work. But I do have 1, 0, negative 1, 50, 0, 1, 2, 10. So I can solve this system. I can solve for y from the second row of this matrix, and I can solve for x from the first row of this matrix. And I'm going to do that and write this as an ordered triple depending on z. All right, so let me write this down so you can see it when I share it. All right. All right. So here in the second matrix is the matrix that I got when I used Gauss-Jordan elimination on that first system. So the second row of this matrix gives me an equation in y and z. And it says that y plus 2z equals 10. So I can subtract 2z from both sides and solve this equation for y in terms of z. So when I move the positive 2z from the left-hand side to the right-hand side, it becomes negative. All right, now I'm going to take the first row and write the equation in x. So I have x plus 0y minus z equals 50. So now I can solve that equation for x by adding z to both sides. So I can move the negative z to the right-hand side of the equation by making it positive. So now I can write my ordered triple, x, y, z. X is z plus 50, y is negative 2z plus 10, and z is z. So that's how we write the ordered triple. So what this says is that depending on what z is, we're going to find x and y from that value of z. So if z is 0, x would be 50 and y would be 10. If z is 10, x would be 60 and y would be negative 10. So depending on what z is, you can find x and y. And that concludes section 6.2 on what happens if you have a system that's inconsistent or dependent and you solve it using matrices and Gauss-Jordan elimination.